so let's pick up again then where we were yesterday. So let's just review the discussion of yesterday afternoon so that we're all on the same page again. So we're in this situation where, at the present moment at least, we have Higgs and nothing else. And of course, we're going to continue to look in all the directions, push up in energy, and try to look for the less standard types of decay modes that might be hiding at the LHC. But nevertheless, I think it's true that naturalness is increasingly challenged, sort of at the 10% level. So I would not say that searching for new physics that solves a hierarchy problem is dead by any means, but certainly naturalness is becoming increasingly challenged. And in some sense, we kind of were expecting that already, because before you're going to be producing a particle on shell, you expect it to show up in loops first, right? So the fact that it wasn't seen in some sense, at least for the 7 and 8 TeV LHC runs, is maybe not that surprising because of the precision programs at LEP in flavor through meson oscillations and lepton flavor violation, and all the searches at Tevatron didn't show any deviation from the standard model, which you might expect to show up from new particles appearing in loops. So then the next question that we asked was, well, what kind of new physics can you look for at the LHC that might not be directly associated with the hierarchy problem? Okay, seems like a logical next question to ask. What kind of new physics at LHC is not associated with naturalness? And for that, we said, well, you kind of need a guiding principle. So we looked at the cases of you can look for heavy types of resonances. So for example, Z prime, leptoquark, new colored states. These are not necessarily associated with the hierarchy problem, and from some motivation might be that, well, the standard model itself is not minimal. So there's no particular reason to believe that whatever you're going to look for at the weak state, at the weak scale, as you push up in energy, is going to be the most minimal thing you can write down, which would be a single standard model Higgs and nothing else. These, on the other hand, are the searches are pretty well designed to look for heavy states, because you trigger on hard leptons or hard jets or other hard objects in the event that make it easy to look for these states. Okay, but we said, well, there might be more challenging signatures in low mass hidden sectors. So we gave the picture that you have the standard model, you have hidden, and there may be a barrier between the two sectors, which is going to be some high mass resonance, which is why you don't just see the hidden sector. This barrier, for example, could be a Higgs, it could be Z prime. It could be any of these states you were looking for just by themselves. But because you're decaying into a low mass hidden sector, the types of signatures that would show up at the LHC could be quite different. On the other hand, it might not be a high mass barrier. Instead, the mediator might just be some low mass, weakly coupled state. That would be connecting the two sectors. But the reason why you don't see the hidden sector is you need some very intense type of intense experiment to look for these very rare types of production of particles in the hidden sector. And so what we said was that we were going to look at, in this general type of setup of looking for hidden physics, we are going to focus on three types of scenarios. So the first one was exotic Higgs decays. And we gave several examples of topologies. For example, you could have Higgs decaying to two neutral particles, and those neutral particles could then decay to a dark photon, which then subsequently decay to pairs of muons. And the dark matter particle, which I'm going to call X, which note that this particle does not reside within the MSSM. So later on, I'm going to construct an explicit model of this type that is motivated. The second thing that we said was we were going to take a look at strongly coupled hidden sectors. So the three examples I said we were going to talk about were hidden valleys, quirks, and unparticles. So we started our discussion of hidden valleys already, and I want to finish this discussion with quirks and unparticles. And then lastly, so here are strongly coupled hidden sectors. I also want to talk about weakly coupled hidden sectors of the type that you might construct, for example, in this kind of process where you spit off a dark photon, a dark weakly coupled photon. Okay. So that's what we're going to continue our way around this, and then finally we're going to conclude this by coming back to the Higgs and looking at the effect of these exotic states on the stability of the electroweak vacuum. That'll be the last subject for today. Okay. So we were working our way through these strongly coupled hidden sectors, and we gave the example of a hidden sector which was had two light dark quarks and a strongly coupled gauge group. So we started with the case of a hidden sector which consisted of a strongly interacting gauge group. Let's just take it to be some SUN. And two light quarks, V1 and V2. And the degrees of freedom then in the hidden sector in this particular model are going to be what again? What are the bound states when I'm at energies below the confinement scale? Huh? Hadrons, yes. What type of hadrons if I have two light quarks? Pions, yes. Thank you. Just wanted to make sure you guys were awake. Okay. Okay, so I'm going to call them pi plus, pi minus, and pi 0. These do not actually carry any electrical charge. I'm just using this plus and minus to denote the isospin quantum number. And then the point was that depending on what the confinement scale is of this gauge group, that is what's going to set the multiplicity of these particles that you produce. So you're going to have some potentially very complicated event. So I'm going to say make a Higgs. And then it's going to decay to 2 of these quarks. I'm going to have a hadronization, and I'm going to spit off a number of these states. Some of these are going to be stable. The pi plus and pi minus have a conserved global quantum number, which is isospin. But these, the 0 guys, are going to decay back through the Higgs to, say, pairs of quarks. And the important thing for the phenomenology of these sectors is that the number of these resonances that you produce is going to depend basically on the center of mass energy of this event divided by the confinement scale. Okay, there are some other factors sitting in there. And to get it right, of course, you need to hadronize it with a tool like Pythia. But nevertheless, you can see that if you're producing these states at pretty high center of mass energy, then you're going to have a very large number of these dark pions. And so, as a result, if you look at the number of hadrons as a function of this, depending on what this confinement scale is, so let's suppose I have 100 GeV resonances, I'm going to produce a fairly small number of these. Okay, so let's take instead the case of production through an even heavier state, a few TVZ prime, which then goes to these and then hadronizes. So in that case, you know, you'll produce, depending on, this is very schematic, to do it properly, of course, you would have to simulate it. But as you decrease the mass of the resonances, of course, the number that you're going to produce goes up. And so you have the potential for producing, you know, many, many of these resonances, of these low mass resonances through this heavy connector state, which then decays down into the hidden sector. And so at some point, as you're lowering the confinement scale, you're getting something that's starting to look more and more like a fireball type of event, where the individual resonances in there will reconstruct to one of these dark pions. And so the phenomenology of these sectors can be quite distinct from the kinds of things that you look for if you're just looking for a few hard objects that reconstruct to heavy resonances. And a few of these searches have been implemented, as we said before, in the context of Higgs searches, where you're only decaying to 2 of these V pions. And I think one of the open questions is whether you can use jet substructure type techniques to try to reduce the backgrounds on these types of signals. And that's something that's an open question. So here we were looking at the case of 2 light flavors where the degrees of freedom are pions, and importantly, the mass of these quarks was much lower than the confinement scale. That's the type of hidden sector that I need in order to get a theory with this type of structure. Of course, because we're talking about hidden sector dynamics, that's really pretty free. There are a lot of other things I can do. and the signatures will look quite different. In this case, because my hadronic degrees of freedom are pseudoscalars, I'm going to decay prominently to heavy flavor. If I just make as simple of a change of taking this 2 light flavor model to having only 1 light flavor, I still have the confining gauge group, SUN, and I'm just going to have 1 quark, light quark. In this case, now I produce the vector resonances as well. So I produce a rho and an eta, for example. And these will decay democratically to leptons as well as to heavy flavor. Okay, so for example, I could have an event where I go through this heavy state, I produce my 2 dark quarks, they hadronize, and the particles that I get in the final state will include things like rhos, etas, sigmas, and so forth. The rhos and the sigmas are vector. This is a vector particle. It can decay to leptons. This is a pseudoscalar. It will decay to heavy flavor. And so in this case, you might be able to actually trigger on the leptons. And in this case, your life becomes easier because you're not only relying on heavy flavor. Okay. Is that clear? Yeah. Okay. I see people generally shaking their heads. Okay, that's good. In the positive direction. Okay, so depending on what type of structure you put into this hidden sector, you can get a very wide range of signatures. So this is the case where I have either 2 or 1 light quark in comparison to the confinement scale of this hidden sector. If instead I make this confinement scale the quark mass heavier than the confinement scale. So I have 0 light quarks, light dark quarks. Okay, all of them are heavier than the confinement scale. This is a scenario that is called Quirks. And in this case, the signatures become even more exotic, actually. So if, for example, I could go through standard model gluons in the initial state, go through these heavy quarks. These heavy quarks then go to dark gluons. I'm going to put a line through them to denote that they're dark. Okay, and this operator is equal to F mu nu hat, or perhaps I should write these as G's because they're strongly interacting. Okay, sorry, why did I write this way? Okay, and because I want to write it this way, that's why. Okay. So what this does then is to take 2 standard model quarks, go through the connector particle now, which is a fermion, and go to this infracolor. In the dark sector. Okay. So now, once I've produced these guys, I can't make these bound states of dark sectoral neutral states. I can't put together a fundamental and an anti-fundamental into a bound state because that bound state is not stable. Instead, what happens as a result is that you get quasi-stable strings. Okay? So if you look at the way that would appear an event at the LHC, I would have a pair of protons. I would pair produce these heavy connector fermions. And those would now go out. And as they go out, you would produce a string between these 2 heavy quarks that you've produced. Okay? Okay. So potentially, now the length of this string, so I can just write down the energy in this string is equal to twice the heavy quark mass. Maybe I should call this m sub v. And then the potential energy that is stored in this string. So what's going to happen is these two quarks go out. They have this infracolor string between them. It's going to stretch until all of this energy, the kinetic energy in the quarks, gets converted into the potential energy of the string. And then what's going to happen is that they'll oscillate back towards each other. Okay? And the typical separation that you'll get between the quarks before they start coming back together is going to be, of course, when this energy goes to 0, which is to say it's going to go like lambda hat on KeV to the minus 2, the mass of this guy in TeV, and the typical scale associated with that is about 10 centimeters. Yes?
For the operator you wrote down, why is it clear that it's suppressed by the dimension of the strong scale and not?
Oh, it shouldn't be. Sorry. Thank you. I was just thinking I went on autopilot. This is not the confinement scale. It's going to be the, well, there's going to be coupling constants in there. So let's just call this lambda v. It's not the confinement scale. Thank you for clarifying that. It's the cutoff associated with integrating out these quarks. Okay? So what happens then is you produce these two quarks. They go flying out. They go for quite a distance until they notice that they're bound to each other. And then what happens is they start oscillating back to each other. And depending on what the confinement scale is for this hidden gauge group, this infracolor, it can be macroscopic distances that would show up as oscillating strings in the detector. So if you look at the way that looks, then you could have, for example, curved tracks recoiling against something, say a jet, just to balance the energy. But you can see these stable curved tracks showing up in the detector, okay, if this confinement scale was quite low. So for example, if you're talking about a distance which is below 1 millimeter and 10 meters, that corresponds to a confinement scale which is between 100 eV and 10 keV. So that's a macroscopic case. You can also have something that looks a little bit still exotic, but potentially more easily triggerable, which is to have these oscillating tracks just recoiling against a jet in the detector. And of course, as you go to higher and higher confinement scales, these oscillations become invisible. Okay? And what it just looks like is a highly ionizing track in your detector recoiling against an ordinary jet or photon. Okay? And so in that case, you can use dedicated searches which look for highly ionized tracks. For example, D0 did a search for these guys. I'll give you the number in case you want to look it up, where you can put a constraint on the mass of these particles which are produced. My understanding is that that Atlas, at least, has a search that they could do that needs a little bit more pushing from theorists in order for it to happen. Okay. So these are fascinating signatures that would not look like sort of your standard heavy physics at the LHC. but nevertheless are potentially detectable, completely consistent with cosmology, maybe not minimal, but then again, neither is the standard model minimal. Okay. So in fact, all of the tricks that we know for constructing hidden sectors from various types of theories, say string theory, can be constructed within these hidden sectors. So we talked about strong dynamics can come in many guises. So we talked about QCD-like theories with some number of flavors and colors. Okay, and these were the first set of signatures that we talked about. You can have QCD flavors with 0 light flavors, but still n colors. Okay, and those are the Quirk type signatures. If you want to expand out into other types of theories, well, you can have one heavy flavor here. You could talk about pure glue theories. You could talk about theories with UV fixed points. Could have an RS throat, KS throat, embedding these specifically within the context of string theories. You might have some type of Seiberg duality cascade. A theory with a Banks-Zaks IR fixed point. Okay, the list would go on. Okay. And if I were going to write this down then in terms of classifying these types of theories, if I write this in terms of the gauge coupling itself, and the running of the gauge coupling, you can classify these purely in terms of alpha and beta. Okay, so 0 beta, of course, is a CFT. I can have small beta, large beta, small alpha n, moderate, and extreme. And all of these theories reside in some place in this table. So I can have a Banks-Zaks theory, which is conformal in the IR. N equals 4 SUSY resides here. These theories called unparticles, which I'll talk a little bit more about next, which were very popular a few years ago, reside here. N equals 4 SUSY. Generic Seiberg, CFT. And at extreme alpha n, you have the RS bulk. Okay. Many things you can do. You have here perturbed Banks-Zaks. I'm not going to write that down. You have unparticles with mass gaps. Perturbed Seiberg CFT, deformed RS bulk. Okay. For example, when you put in an IR brane within RS, then you break the conformality of the theory. Okay, but it's still coming at very large alpha n. In this case, if you have a small alpha n but a large beta, that's not going to last. Pretty soon, the small alpha n becomes large. This is QCD in the IR, has a large beta function but a moderate alpha n. And in this case, the RS-IR brane is exactly where the running now starts to become large. Okay? So there are all types of theories that you can fill out in these hidden sectors. And let me just go through one more example. So we went through the case of the QCD type theory and the theory with the quirks, which were heavy. I want to talk about this class of theories that saw a burst of activity a few years ago, these unparticle theories. And these were theories that were supposed to be conformal in the IR. And so as a result, because they were conformal in the IR, the mass gap between the particles that you would produce in the hidden sector was effectively zero. And so what would happen is that instead of producing these states, for example here, which could then decay back to the visible sector because they were massive, all of these states, these unparticled states that you would produce in the hidden sector would just disappear as missing energy. Because their mass gap, it was a purely conformal theory in the IR, their mass gap was zero, and hence stated in terms of particles, the masses of the particles were zero. Okay, so let me just rephrase this in terms of language of particles by looking at a theory that we know is conformal, and then seeing how the presence of the IR brane breaks that conformality explicitly. Okay. Okay, so let's look at a conformal hidden sector. So at least to start, we're not going to put in any type of confinement scale, the confinement scale, of course, being what sets the mass gap between the states and the theory. And we're going to look at this conformal hidden sector by setting up an RS type theory with this metric. Okay, so it's conformal because, as you can see, you take a rescaling, which is z goes to alpha z, and x goes to alpha x, and the metric remains the same. And this is the same type of setup as in an extra dimension with a UV and IR brane. Okay. And as ZIR goes to infinity, you regain the conformality in the IR. Okay. So let's just look explicitly at the particle spectrum of this theory with particles in the bulk. Okay. And see how it behaves and compare it against the hidden valley type theory that we were looking at earlier. Okay, so I can write down a Lagrangian for these fields in the bulk. Which is this. And now I can write down the equation of motion for this field in the z direction. So I want to get the profile. Q squared is just the momentum in the 4 dimensions. Acting on phi is equal to 0. Okay. So just a couple steps of algebra there. And if I make a redefinition, which is phi is z to the 3/2 psi, then it falls into a nice form. So if I make this definition between psi and phi, then the equation of motion reduces to this. And if I take the large z limit, okay, so taking z sub IR fairly large, looking at the behavior near the IR brane, then the solutions to this guy is just a usual wave equation, okay? And the solutions to this are just that psi is equal to sine of mz plus a constant, where I'm now replacing the momentum there with the mass, okay? And if I go ahead then and quantize this, with the boundary conditions on the branes, then what I end up with is that m sub n is 1 on z IR times pi n minus that constant. Okay? So what that's telling you is that this conformal hidden sector with this setup with 2 branes, just as in IR, becomes like a theory with the mass gap between the states set by the location of the IR brane. And in fact, this is the only mass scale in the sector. So what the spectrum looks like, if I look at the mass then, is I have a bunch of evenly separated states with this separation set by z sub IR. Okay, so this is an analog with a strongly coupled theory where the mass gap and the separation between the scales is set only by the confinement scale. Okay. So then you might ask the question, well, QCD, for example, doesn't behave exactly like that because it doesn't have just the confinement scale. It also has the quark masses in the theory. So if I want a theory then now that looks like a conformal theory that I've explicitly broken the conformality with an IR brane, but now I want to have a theory which actually looks more like QCD in that I have a mass gap and then the states above it are set not by this mass gap but by another scale. So how would you set that up within this two-brane theory? Okay, so that's actually very easy to do with the analog of a Higgs. delta m squared.
Law of this kind of stringy type.
Yeah, that's right. Yeah, but it's again fixed by the yeah. So let's see whether we can get this type of setup out of this theory. So let's add, as I said, a term to the Lagrangian, which looks like h phi phi. And furthermore, this Higgs-like field is going to have a profile in the extra dimension. It's going to have a profile which looks like m squared z squared. So it's very peaked towards the IR brane. So if I do that, I can just add that into my equation of motion. And then my equation of motion is now modified with this new mass scale now, which is going to set the mass gap. All right, so now, because I have this additional term, this fixed mass term, as a result, what happens is now my masses are going to be q squared minus m squared times pi n minus that constant. And therefore, as 1 on ZIR goes to 0, which is to say as q squared goes to 0, the mass gap doesn't vanish. Okay, so what I end up with then is this, where now this is set by this scale that I put in by hand, and these states now are split by 1 on ZIR. Okay? So I can maintain a mass gap in the IR, but keep the theory conformal as I go to higher resonances by taking this IR brane off to infinity. Okay? Yeah. Yeah. Sorry, what? Yeah. Yes. That's it was sort of implicit there. Yeah. Exactly. 1 on ZIR. Okay. So this is a way to take one of these extra dimensional theories now, which are the analog of the QCD theory, to set it up and then dial the mass gap and the splitting between the states independently and reproduce the phenomenology that I might see from a QCD-like theory. Okay, so this is just an explicit way to see how there's this usual duality between extra-dimensional theories and strongly coupled dynamics. And I wanted to demonstrate it here specifically within the context of these hidden sector theories. Okay. So this is going to conclude then the discussion I wanted to have about the strongly coupled dynamics in these hidden sectors and the different types of hidden sectors that you might be able to construct and the types of dynamics that might show up there. So before I go on to talking about weakly coupled hidden sectors, does anyone have any questions? Hopefully that means it was crystal clear. Okay. All right, so I don't want to give you the impression that the only place that it's interesting to construct hidden sectors is through strongly coupled theories. There are actually very well motivated theories within the context of supersymmetry. So if you believe that supersymmetry is still hiding there, somewhat above the TeV scale, we're perfectly happy with 10% or even 1% fine-tuning, then hidden sectors actually give rise to qualitatively different types of signatures, even for just supersymmetry at the LHC. So I want to go through some model building examples of how that works. So supersymmetry is, usually what you look for is the production of strongly coupled states, just because the rates are much higher than for the production of weakly coupled states. So you might look, for example, for the pair production of gluinos at the LHC, which will then cascade down in very familiar form down to the LSP, which I'm going to refer to as the LOSP from here on out, the lightest ordinary supersymmetric particle. And on their way down, they spit off a few jets, maybe some leptons, if the theory is nice to you. And so you trigger on these hard objects plus usually fairly hard missing energy in these events. Okay? And the experiments are becoming as we've seen, more and more sensitive to these, the masses of these particles. Now, on the other hand, what I've said is that in addition to whatever might be in that peak, these, say, heavy states like gluinos and quarks, you might have a hidden sector which is sitting alongside the theory. And so you can decay down into the hidden sector. Let's just give a simple example of a LOSP decay through a dark photon to some hidden sector particle, which then perhaps decays this way. Okay. And we already saw an example of a search like this with the Higgs mediator actually being the particle which decays to the neutralino, which subsequently decays. What might happen instead is that you just get an extension of this cascade through this dark photon and spit off less missing energy plus a couple of leptons. This signature is actually really pretty good because you have a couple of leptons, additional leptons, that'll reconstruct to a light resonance. This is not too hard to look for. So you can ask the question, well, why do this? What does this get for you? Well, first of all, it may just be the case that you have hidden sector particles, which are much lighter than this SUSY breaking scale. And I'll give a motivation for theories later on for why there might be dark matter that's much lower mass than the weak scale. On the other hand, if you just think about the structure of supersymmetry breaking, SUSY breaking is always communicated to the visible sector. So there's some mechanism, it's either gravity or gauge mediation, which communicates SUSY breaking, clues it into the visible sector. Okay? And the strength of the interaction between the SUSY breaking and the visible sector, of course, is what sets the scale for the superpartners. On the other hand, if I have a dark sector, it may also communicate with the SUSY breaking. And its scale does not necessarily need to have the same strength coupling to the SUSY breaking as the visible sector does. So if the coupling of the dark sector to SUSY breaking is smaller than what the visible sector sees, then the mass scale in this dark sector is just naturally going to be smaller than what it is in the visible sector. Okay. There's another type of construction that's quite similar to this, which is that you have SUSY breaking which is communicated only to the visible sector. So you have SUSY breaking, which goes to visible. And then the dark matter sector, for one reason or another, doesn't see SUSY breaking very strongly directly. It only sees it through its coupling to the visible sector. Okay? If this coupling is small, okay, it doesn't even necessarily need to be small, because there may be loop factors. It's quite natural, again, for the SUSY scale in the dark sector to be smaller than what it is in the visible sector. Okay? And in that case, the dark matter, of course, because it has its mass scale set by the SUSY breaking, is not at the weak scale. Okay? So what are the various types of effects in these two types of setups that you can have? Well, they really go along the lines of the different types of SUSY breaking. So you can have supergravity effects to start. And gravity effects are going to not discriminate between dark and visible unless the dark sector is sequestered from the visible sector. So generically, that's just going to communicate a certain amount of SUSY breaking to all sectors, which is on the order of the gravitino mass. Okay, this for the for the most part, except for the special cases, is just going to be to all sectors, unless you have a dark sector which is sequestered. And in that case, the mass that you get, and this would be an anomaly-mediated type scenario, is going to be a loop factor down from the gravitino mass. Okay, so it's possible for the SUSY breaking scale in the dark matter sector to be a loop down from the visible sector. And interestingly enough, a loop down from weak scale is about a GeV. And there are reasons why the GeV scale might be motivated for dark matter reasons alone, which I'll talk about in a little bit. Okay. So you can have these gravity and anomaly-mediated effects. You can also have gauge-mediated effects. So that mass that you get, soft mass, goes like the gauge coupling on a loop factor times F on M, okay, which is about, it's going to go like the ratio of M Planck on M in comparison to the M3 halves. Okay? And depending on which of these effects is dominant is going to determine what the dynamics looks like in the hidden sector. Okay. So let's take an example, a concrete example, which has been very popular in recent years. And I also want to make connection to the second type of hidden sectors, which is where you have a low mass, weakly coupled connector between the two sectors, and that is when you have the communication going through kinetic mixing. Okay, there's been a lot of discussion in recent years about communication between visible and hidden sector via kinetic mixing. So let's just take this as an example and take look at a Lagrangian which has a superpotential, a Lagrangian which is a mixing between hypercharge, which I'm going to call B, and I'm going to call the dark gauge group X. Okay, and this has a mixing parameter epsilon. Epsilon is usually induced via integrating out some heavy particles, which are charged under both hypercharge and the dark gauge field. And so a natural scale for this is a loop factor, so on the order of 10 to the minus 2 to 10 to the minus 3. Okay. So you might have a loop factor sitting here, which mixes the two, but then you have the usual kinetic terms for the two fields. Okay. So what do you get out of this theory? Well, this kinetic mixing between hypercharge and the dark matter automatically induces a breaking of the dark U1 symmetry. So let me show you how that works. So let's look at the potentials. I'm going to have a dark Higgs, which is charged under this dark U1. I'm going to write down the potential for this. So this is for the dark Higgs. I'm going to, it's proportional to the dark coupling constant, which is, I'm going to call G sub x. A sum over all my dark Higgses, which I'm going to call phi, which have a charge x under the dark U1. And then this is the interesting piece. This kinetic mixing term induces a D term. This is the hypercharge D term. The hypercharge D term is minus gy on 2 cos 2 beta times v squared. So this is the term that arises within the MSSM, hypercharge D term, okay, where G sub y is the hypercharge gauge coupling constant. And this mixing induces this term in the potential for the dark Higgses. And the consequence of this is that it induces a VEV for the dark Higgses. So automatically, you just end up with a VEV for the dark Higgses, which is epsilon psi y on G sub x times the charge. Okay. So what you notice is if this is 246 GeV, and this epsilon is on the order of 10 to the minus 3, what you find is that you induce a VEV for this field which is around 10 GeV. Okay. So what actually happens then in a hidden sector? Then why should I care about setting this mass scale at around 10 GeV? So let's look at a specific model for this. So now I have a field phi with a VEV around 10 GeV, and let's look at a specific model which is a superpotential, which is the NMSSM. And then I'm going to take the dark sector Higgses, which I'm going to call H and H conjugate. Okay, so that these fields here would be H and H conjugate, and then we're going to put in a singlet again, put in some coupling lambda. And for this particular theory, I'm not going to go through the details of it. What happens is that this induces a VEV for H. H conjugate and S do not obtain VEVs. And as a result, you end up with a potential which looks like lambda squared H squared H conjugate mod squared plus S mod squared plus lambda squared H conjugate mod squared S mod squared, and then the gauge piece. I think this is the longest equation that I'm actually writing out during these entire lectures. Okay. Conjugate mod squared minus psi, where psi is this combination. Okay. And then this, of course, has to get squared. So this is the potential. I'm not writing down the potential for the visible sector. It can take care of itself. It doesn't notice the dark matter sector. But this is what I have in the dark matter sector, and this is the total potential. And so now what you can see is that H picks up a VEV from this hypercharged communicated D term. But neither this field nor this field pick up VEVs. And so you can just read off the spectrum from this potential. We'll call the VEV of H eta. Okay, and then you can read off the fermion mass matrix. Okay. This is what the mass matrix for the fermions in this basis. So this is the dark gaugino, the dark Higgsino, and the dark siglino. So if I were just to draw a picture then of the spectrum, well, let me fill this out then. In the particular case where SUSY breaking is not dominated by gravity mediation, but it's dominated by gauge mediation. So I'm going to take the gravitino mass much lighter than the SUSY breaking scale. So we're going to take the gravitino mass much, much smaller than the typical mass scale that's communicated via SUSY breaking to the dark matter sector. And in that case, my spectrum, in the limit that I take this dark coupling constant, much bigger than lambda, takes on the following form. I'm just going to draw a picture of how it gets split. So I have the gravitino down at the bottom. Then, because I'm taking this gauge sector much bigger, sorry, I wrote this in the wrong direction. Gx much smaller than lambda. Then I have the gaugino sector along with one of the Higgses. And up here, I Higgsino-Singlino mix. I have the singlet scalar, and this is the Higgsino, and I have the Higgs scalar. Okay. So you can check this. Okay. So what I end up with then is a Higgs sector that's sitting up here around 10 GeV. Its mass scale is set by this loop suppressed mixing parameter, which is around 10 to the minus 3. This hypercharged D term, which sits around the weak scale. And that sets the masses of these particles up here, which are in this lambda sector. Their masses are set by lambda times the VEV of the one scalar that breaks. And then I have the gaugino sector here, which is somewhat lower in mass. The ratio of the mass scales is going to depend on what the ratio of these couplings is, but let's set this around a GeV. And then I have the gravitino there sitting at the bottom. Okay. Now, why might I do this? Well, there are two dark matter motivated reasons which I'm going to give. One has to do with the usual thermal freeze-out calculation, and one does not. So here, let's suppose that gauge mediation is dominant. So SUSY breaking is being communicated to the visible sector via visible gauge coupling constants. So let's just write G weak here. On the other hand, if SUSY breaking is being communicated to the dark sector directly via gauge mediation, then this is being communicated with a strength G sub x, right? Because the diagrams that are entering in here are that you have your particles which are receiving SUSY breaking masses through, for example, two-loop gauge-mediated diagrams, and these couplings sitting here are gauge couplings. Okay, so the typical mass scale then is set by is going to go like this coupling constant to the fourth. You have some 16 pi squared and whatever SUSY breaking you have, F on M. Okay, and we're going to just write this as M soft squared. Okay, all right. But of course, if I'm communicating SUSY breaking directly to the dark matter sector, instead of having G, I'm going to have whatever the dark gauge coupling constant is, but a common mass scale for SUSY breaking. Now, what's interesting about that is you guys all know about the standard thermal WIMP freeze-out paradigm, right? Where the number density is set by the annihilation cross-section. The annihilation cross-section is going to go like, so for example, if I had neutralino dark matter, this is the most vanilla thing you can write down, annihilating to WW or ZZ. Okay, that annihilation cross-section is going to go like G weak to the fourth over M dark matter squared. So let's call that M viz squared, okay? And taking this to be around a TeV and this to be the weak coupling constant, you get about the right relic density. Now what you notice is that it's exactly the same combination that enters in both cases. If I just take the ratio of these two from this gauge mediation, I actually preserve the WIMP miracle, even though the dark matter could be much, much lighter than a TeV. Okay, so if I just look at that and plug this in, then because this scales, mvis squared, so gx to the fourth on mvis squared, which is what enters into the WIMP miracle, goes like 16 pi squared on m soft squared, which, by this gauge mediation argument, scales exactly the same way as g to the fourth. Sorry, I should have. I'm mixing up the labels here. Okay. That argument was more confusing than it should have been. Okay, but the point is here that exactly the same combination of couplings and masses enters into the soft masses that you get from gauge mediation as enters into the annihilation cross-section that you would get from a WIMP miracle type of argument. Okay, so that implies that if you get the correct relic density from taking g weak on 1 TeV squared, that means if this is true from gauge mediation, then I should also get the correct relic density here too. Which effectively means that you're trading off a smaller coupling constant for a lower mass in the right proportion. Okay. So that's one reason why these hidden sector models may be well motivated. I want to give you a second motivation. Why dark matter may be a loop below the weak scale. Okay. And that is this observation that the ratio between the dark matter and the baryon densities, observationally, the energy densities, are about a factor of 5. Now, the baryon density is set by the baryon-antibaryon asymmetry in the universe. So it's the proton mass times the primordial asymmetry between baryons and antibaryons, which is set through some baryogenesis mechanism. Okay. On the other hand, in the usual type of WIMP miracle argument, this density is set by an annihilation cross-section. So this is usually set by some physics, which is maybe baryogenesis or leptogenesis. Pick your favorite model. This, on the other hand, so you're going to have CP phases and the strength of the first order phase transition, the dynamics of outer equilibrium decay, all of those things will enter into baryogenesis. On the other hand, what sets the dark matter density is this annihilation cross-section. So a priori, there's no real reason why these should be related to each other, it would seem. Why are they so close to each other? So you might say, well, maybe there's some type of mechanism that actually relates this dark matter density to the baryon density. And instead of having dark matter being able to self-annihilate, instead what I have is actually a cosmic asymmetry of dark matter versus anti-dark matter. Okay? That's not the usual scenario. Usually what we say is that that the dark matter is not asymmetric at all. It's actually is able to self-annihilate, and there's no cosmic asymmetry. But you can posit instead that there might be some mechanism that relates the two. And if there's some mechanism that relates the two to each other, that puts them basically in chemical equilibrium, what that actually implies from this relation is that the natural mass scale for the dark matter is around 5 times the proton mass. Okay? Namely, a loop below the weak scale. So what that would imply then is that depending on what the mechanism is for relating these two to each other, I can actually have decay of the loss, the LSP, the neutralino, or whatever it is, into the dark matter sector, which is residing just below that scale. So what would be the types of decay mechanisms? Well, you would want the same type of mechanism that relates the asymmetries to actually mediate the decay at the LHC. So how is it that I set these asymmetries related to each other? Well, there are a number of different ways of doing it. One very simple way is to take combinations of standard model fields that carry baryon or lepton number but are a singlet. And there are a limited number of things you can write down. For example, if I take all right-handed fields and write down a neutron, that carries baryon number but is a singlet. I can do the same thing with a quark doublet, a lepton doublet, and a right-handed field. I can do the same with two doublets here and a right-handed field. All of these carry baryon number or lepton number, but carry no gauged standard model quantum numbers. And now what I can do is to take my singlet field, and I can just sandwich it here. I don't care how many powers. I'm just going to put some power s to the n in front of this operator. I've put s to the n power fields here. What that does is communicate whatever chemical potential might be sitting in these fields directly to the dark matter itself. Okay? And so now, if I'm embedding this within the context of supersymmetry, this type of mechanism can set the mass scale for the dark matter. But now, what's setting its density is actually the cosmic asymmetry itself. Okay? And so what you end up with then is that this field sitting in here is actually naturally the dark matter. Okay? So I wanted to give you two classes of models, and what's going to happen now, let's suppose you had a neutralino LSB. So it depends on what operator you pick up here. So if I had a neutralino LSP, and let's suppose I had this operator, the neutralino now will go to a jet and a squark, and the squark now will go to 2 quarks and this dark matter particle, which here I called S. I could have well called X. Okay. And so as a result, you get reduced missing energy, because all the missing energy that would have been sitting in this neutralino now gets shared between these 3 additional jets plus the MET. This MET, but it's reduced MET. So if I have some type of cascade decay, which is already involving multiple jets upstream, what I can get then is a signature that looks sort of like RPV. Okay, so I'm taking an RPV type operator, but I actually pick up a reduced amount of MET. Okay? So that's going to conclude what I wanted to say about weakly interacting hidden sectors and the types of signatures that you can get at the LHC. I wanted to spend a few minutes actually coming back full circle to the Higgs, in particular talking about what dark matter can do to vacuum stability for the Higgs. So I'm going to have to sort of rush through this, but I think it's an important enough point that I'd like to spend a little bit of time on it. Move this up. So the electroweak vacuum is not guaranteed to be stable. So we're told this story, which is that the standard model Higgs potential looks like a wine bottle. And so you drop into this absolutely stable minimum, and the universe just sits in this absolutely stable minimum for forever, okay? Now, this is actually not totally true, because what can happen is that the running of the coupling constant, the quartic coupling constant, can actually go negative at large VEVs. Okay? So in fact, if you write down the beta function for the quartic coupling constant, what you notice is that the coupling to the top has a tendency to drive the quartic coupling smaller as you go to larger scales. Okay? So the vacuum expectation value is mh squared on lambda. So as you increase the Higgs mass, the quartic has to go up. Okay? And the point is that if this quartic is too small at the weak scale, as you evolve this thing up to higher scales, it can actually go negative. Okay? And so the issue is then, if I plot this in the mass plane, what this looks like is, I look at the observed Higgs mass versus the scale, which I'm just going to write as lambda. At very high Higgs masses, you start out with a large quartic in the IR. And so even though the top is causing it to get smaller, it doesn't actually go negative. Okay? Any time between here and the Planck scale. Okay, so up here, large enough Higgs, you've got a large enough quartic, and so the thing is absolutely stable. As you drop into lower Higgs mass, the quartic starts to go negative, but nevertheless, if you're sitting down here in the electroweak vacuum, you still have to tunnel through this barrier in order to get to the unstable minimum. And so there's a tunneling time that's associated with this, and as long as that's larger than the lifetime of the universe, you would say you're not too bothered by the fact that, technically speaking, the electroweak vacuum is unstable. Okay, so you're still okay. Phenomenologically, you're still okay, but you're in this metastable region. And then once you go to small enough coupling, quartic coupling, then you're just unstable, and this region is ruled out. So if you look at these masses, now if you're going to make this, say, 10 to the 7 GeV, going all the way up to the Planck scale, 125 GeV sits right about up here. It's right on the stability metastability boundary. Okay? So really, we're in okay shape. If we're not absolutely stable, then we're at least metastable, and the implications for phenomenology, as far as we care, should be basically null. And if the Higgs had been, say, at 110 GeV, then what that would tell you is that in order to save the electroweak vacuum by our existence proof, new physics would have to enter at some intermediate scale in order to fix this problem. So you can flip this around and say, well, if the Higgs were lighter, it would actually be evidence for new physics, that there has to be new physics well below the Planck or the gut scale. Okay? Now, This is with just the standard model and nothing else. On the other hand, we know there's dark matter, for example. And the dark matter may be minimal, it may be electroweak, it may couple to the Higgs. As a matter of fact, all the searches that we have in direct detection experiments are really aimed at looking for dark matter that interacts with ordinary matter through the Higgs. Okay, so you can ask the question, well, let's suppose dark matter interacts with the Higgs. What happens? Well, let's look at dark matter that couples in the following way. So let's look at dark matter which is a mix of an electroweak doublet and an electroweak triplet. So the D is the doublet, the T is the triplet, in a use of obvious notation. Okay? And the way it's going to annihilate is via the Higgs. Okay? And so as a result, these couplings of the dark matter, so this is also like mixed Higgsino, we know dark matter. So this coupling to the Higgs, as we've said before, can actually lead to instability in the electroweak vacuum. And in fact, if the dark matter is a fermion, as it is in this case, you can actually push yourself from the region on the stable to metastable band into the unstable band. And in fact, it doesn't take very big coupling constants to do this. So this will be the last thing that I will draw. If you plot the cutoff in GeV, okay, take 125 GeV Higgs. Let's take a sort of modest Foucault coupling. Then what that actually implies is that there has to be new physics at or below 10 TeV in order to not bump over from into this unstable region for the electroweak vacuum. Now, a priori, you don't know what the size of these couplings has to be. However, we do have a way of setting this density via weak-scaled freeze-out. So you could annihilate through these Higgses two standard model states, and that could actually fix the size of this coupling. So if you put in that information, I actually have a plot here for triplet doublet. What you find is that if you want to set the correct relic density of this particle, that the scale at which new physics must enter in many cases has to be as low as 100 to 1,000 TeV. Now that's not directly reachable with collider experiments. On the other hand, that is probable with intensity experiments, flavor types of experiments. And so in principle, these types of physics could show up indirectly in intensity types of experiments. Okay, so there's much more I could say about that, but I'm over time, so if you have questions, why don't you ask them?